moving along in our chapter, we're going to talk about applications of first-order linear differential equations. And this first example we're going to deal with talks about motion with resistance proportional to velocity. And so you guys are probably familiar with force equals mass times acceleration. And in this situation, we might think of it as force equals mass times, now recall that acceleration is the derivative of velocity, so dv dt. And if the resisting force is proportional to the velocity, we can say that m dv dt is equal to negative kv, or rather, dv dt equals negative kv over m. This is a separable differential equation, and it represents exponential change. So using this separable differential equation, which represents exponential change, the solution with an initial condition, which we can satisfy or set as being v equals v sub 0 at t equals 0, is given by v equals v sub 0 e to the negative k over m t. And this was talked about in a previous section in our book, section 7.4. So if we want to determine how far something will coast, and so when we talk about coasting, we're talking about, you kick a skateboard and you let it go and you see how far it goes until it stops. So how far something will coast. We're going to solve the initial value problem, the IVP, which is ds dt equals v sub 0 e to the negative k over m t, when s of 0 equals 0. So s being our position function, v velocity, initial velocity when we talk about v sub 0. So to continue solving this, we're going to integrate on both sides with respect to t. And if I take the integral with respect to t, I end up with s equals the integral of v sub 0 e to the negative k over m times t. And that integration is going to be negative v sub 0 m over k e to the negative k over m t plus c. So to solve the initial value problem, we let that be equal to 0, and we plug in 0 for t. So we end up with negative 0t, and anything to the 0th power is equal to 1. So this term is going to go away, and we're going to end up with v sub 0 m over k equals c. So we can develop a position function, which would be s of t equals negative v sub 0 m over k e to the negative k over m t plus that c value, v sub 0 m over k. And at this point, we can factor out that common factor. So I'm going to skip to the next page and rewrite our position function. S of t equals v sub 0 m over k. And we have 1 minus e to the negative k over m t. So furthermore, what we can say is the limit of S of t as t goes to positive infinity. So as t becomes exponentially large, and then also, since k and m are both initially positive, we can say that negative k over m is always going to be less than 0. Then we know that e to the negative k over m t approaches 0 as t becomes infinitely large. So we can say then the limit as t goes to infinity of our position function is going to equal the limit as t goes to infinity of v sub 0 m over k times 1 minus e to the negative k over m t. And since we just said up above that this would go to 0, we have just 1 there in our parentheses, and we can say that the limit as t goes to infinity of v sub 0 m divided by k times 1 is just going to equal v sub 0 m over k. And this now represents our steady state value. So what we can finally say is the distance coasted equals v sub 0 over m divided by k, which was our upper bound. And this is true in life. If m is large, something is going to coast further, and m obviously referring to mass. So let's do an example to see how long it's going to take for this coasting ice skater to come to a complete stop. So the ice skater's 192 pounds. We are told what our constant k is. It's about 1/3 slug per second. We know our mass, 192 pounds divided by 32. Her mass is 6 slugs. And we want to know how long it will take the skater to coast from 11 feet per second to 1 feet per second. And then how far will the skater coast before coming to a stop? So this is a 2-part problem. So a couple things. We know our mass, 192 pounds. And when we convert that to slugs, we divide it by 32. So we've got 6 slugs. We're also given that k equals 1/3 slug per second. And I know we mentioned this in class before, but a slug is just a different measure of weight. So the first thing we're going to do is to set up the equation. We can say that velocity, ds dt means velocity, it's the derivative of position, equals v sub 0 e to the negative k over m t. So we're looking for an end velocity of 1, and we have an initial velocity of 11. K is 1/3 divided by that 6 slugs for her mass. So I have 1/3 divided by 6 t. And then I have 1 equals 11 e to the negative 1/18 t. So that tells me 1/11 equals e to the negative 1/18 t. To solve this and to isolate t and find out how long, We'll take the natural log of both sides. Taking the natural log of the e just leaves me with negative 1/18 t, and then we would multiply. So negative 18 natural log of 1/11 equals t. And this is the same as saying 18 natural log of 11 equals t. It's just different notation. You should feel comfortable converting between both of those natural log versions. And when you plug this in your calculator, you get that t is approximately 43 seconds. When I type it in my calculator, I get 43.16211,491. So what this is saying is that it takes the skater 43 seconds, roughly, when she starts coasting at 11 feet per second, that's her velocity, to reach a slower velocity of 1 foot per second. So the second part of our problem here says, how long will it take for her to stop? And so one thing we know we can determine is that the distance coasted equals v sub 0 m over k, which is that steady state value we talked about as we were deriving how to solve this problem earlier in this video. And in this situation, we can plug in the values we know. We've got 11 for the velocity, 6 for the mass, over that 1/3 for our constant, and we end up with the distance coasted is 198 feet. So that was as far as she was going to possibly go until she stopped.